Okay, so here is the final video in our series talking about eigenvalues and eigenvectors. Okay, now a definition of eigenvalue. A transformation from a vector space to itself has a scalar eigenvalue. Here, let me get my pen going here. Has a scalar eigenvalue, lambda. Now lambda is a scalar number, could be real or complex. But the transformation has an eigenvalue if there is an eigenvector. This symbol is a zeta, or Greek z. If there's a vector in the vector space V such that the transformation applied to that vector is equal to that constant value, that constant eigenvalue, times the vector. So in other words, the transformation acts on this eigenvector as a scaling. If zeta goes in this direction, then the action of the transformation on zeta will tend to scale this along the same direction. If lambda is bigger than 0, then the transformation will scale the eigenvector up. If it's less than 0, if it's greater than 1, it will scale it up. If it's between 0 and 1, it will shrink it. If it's negative, it will make it go along the negative direction. But however the eigenvalue is, an eigenvector is always scaled by the corresponding linear transformation. Okay. Right, now, a square matrix has a scalar eigenvalue. Now notice this is a transformation from a vector space to itself, so it is represented by a square matrix. We can define the eigenvalue of a square matrix directly, and the definition is similar. Basically, if we consider the square matrix as the matrix of a linear transformation, then the eigenvalue is the eigenvalue associated with the corresponding linear transformation. T times zeta is equal to lambda times zeta. So it's really the same definition, only here we're applying it to one particular representation of the transformation. Let's look at an example. Here's a 2 by 2 matrix. Now, notice if we multiply D by 1, 0, you're going to get 4, 0. If you multiply D by 0, 1, you're going to get 0, 2. All right, so that illustrates this rule for eigenvectors, that the matrix times 1, 0 is 4 times 1, 0. So 1, 0 is an eigenvector corresponding to the eigenvalue 4. The matrix times 0, 1 is 2 times 0, 1. So 0, 1 is an eigenvector corresponding to the eigenvalue 2. Okay, so this makes the point that I mentioned on the previous page, that for eigenvectors, the transformation acts in a particularly simple way, simply by rescaling the vector along the same direction. Now, notice that with this linear transformation, it's not true that every vector is rescaled. If we take 1, 1, which is actually the sum of those two eigenvectors, we get, when we apply the matrix to it, we get 4, 2, which is not a scalar multiple of 1, 1. Because this 1, 0 is scaled up by 4, this 0, 1 is scaled up by 2, they're scaled up by different amounts, so we don't get a vector that's a scalar multiple of the original vector. Okay, it turns out that matrices that are similar have the same eigenvalues, but do not necessarily have the same eigenvectors. In fact, usually they don't. All right, so here's a particular matrix T. This is a diagonal matrix. And here's another matrix, and it turns out, as you can verify, now he worked this out in the background, that if you take P times T times P inverse for this matrix P, we get the matrix S. Okay, so let's see how the eigenvectors are related. Notice that the eigenvectors of T, what are the eigenvectors of T? Look at it for a second, see if you can see what they are. Well, notice if we multiply T by 1, 0, 0, then I get 4 times 1, 0, 0. So this is an eigenvector with eigenvalue 4. If I take 0, 1, 0 and multiply by the matrix T, I'm going to get 8 times 0, 1, 0, so this has lambda equals 8. And similarly, the vector 0, 0, 1, then multiplied by the matrix, I'll get lambda equal 12. Notice that whenever you have a diagonal matrix, then the eigenvectors are going to be the standard basis vectors, because that's just how it's set up to be. All right, so here we have eigenvectors and eigenvalues for t. What about the eigenvectors and eigenvalues for s? Let's see how this works out. This is exciting. Okay, now here is how we represent the action of this diagonal matrix T. It multiplies the first component by 4, second by 8, third by 12. That's in the that's for this standard basis for this transformation given by this matrix T. Okay. Okay, and we can see that here are the three eigenvalues that I mentioned. Here he's showing what I mentioned before, that 1, 0, 0 is eigenvector with eigenvalue 4, and the others are similar. Okay, now let's do our usual diagram that relates the transformation in the standard basis to the transformation in another basis. And we can find a basis such that the transformation is given by the matrix S. Okay. All right, now we can easily find the basis B. How do we do that? Since P inverse is the representation of the identity, okay, so let's go back and see why it is true that P inverse is equal to the rep BE3 of identity. We're trying to get this matrix S in the following way, PTP inverse. Now, in order to make this correspond to this diagram, remember that these PTP inverse corresponds to transformations applied successively. We're getting S going from here to here, and this representation represents S from here to here as the same way as going here to here to here. So this PTP inverse corresponds to going around Robin Hood's barn this way to arrive at the result directly from S. Okay, so remember, you work from right to left when you apply mappings. P inverse is the transformation that's applied first, then T, then P. So P inverse must correspond to this stage in the diagram. T corresponds here, as we see. Here's T, and P must correspond to here. Okay, so this is P inverse, this is T, and this is P. Okay. And we see that this works because this is the inverse transformation of this transformation. Okay, so how do we find P inverse? Well, whenever you have a representation of an identity from one basis to the standard basis, that is easy to find. The columns of the representation are equal to, by the original formula for representations of linear transformation. It's given by the representation with respect to the range basis of the transformations of the domain basis vectors. Okay. Now this representation with respect to the standard basis is particularly easy. It's just the vector represented in ordinary coordinates. Okay, so with respect to the standard basis, any vector is represented by itself. Okay, so the first basis element B1 is the first column of P inverse. Okay, so we can go back and see what P inverse was. He worked out P inverse here. So this is the first basis vector in my basis B. This is the second basis vector. This is the third basis vector. Okay, so this transformation P inverse corresponds to the transformation from this basis representation B to a representation in terms of basis of the standard basis. Okay, so here we have it. This is our basis. These are the columns of P inverse. Okay. All right, now, since each represents the transformation T, that means both S and T represent the transformation T, the matrices T and S reflect the same action. E1 goes to 4E1. So here we should have a T here because we're talking about how the linear transformation T will take the standard basis E1 to 4E1. We also have E2 goes to 8E2, and we have E3 goes to 12E3. We saw that from the form of the matrix. Now we can write these three equations and represent them in terms of the standard basis, which is really what we already did. If we represent the linear transformation T with respect to the standard basis and apply that to the representation with respect to E of the vector E1, then we end up with 4 times E1. Now what he's saying here is simply that the fact that 4, 8, 12, which is the representation of T with respect to E1, times E times 1, 0, 0 is equal to 4 times 1, 0, 0. So that's what he's talking about here. Let's express this same relation in terms of the B basis. We're representing the same transformation, so the same result holds, but the way it's represented is different. The coordinates of representation are different. Okay? So if we represent the T transformation with respect to the B basis and multiply that by the representation of E1 with respect to the B basis, that should give us the same result on the representation of E1 with respect to the B basis. So we should get 4 times E1, because as I said, here we're just representing the same transformation with respect to different bases. Now we know what the representation of T with respect to B is. That's the matrix S. And this we can compute, the representation with B with respect to E1. Okay. All right, so let's see how this works out. The T times so here we're saying what he says up here, that T times the representation of E1 is T times 1, 0, 0 equals 4 times 1, 0, 0. Now S times the representation with respect to B of E1. Now what's the representation with respect to B of E1? Well, let's remember that the representation with respect to bases E3B of the identity, there's this fundamental formula. This is equal to the representation of E3, representation of E1 with respect to the B basis, the representation of E2 with respect to the B basis, and the representation with respect to B of E3. That's our usual formula, that the columns of the representation matrix are the representations of the, let me see if I got this backwards just a second. No, this is correct. As I said before, the columns of this representation matrix are the representations of each individual domain basis vector in terms of the range basis. So this is a correct statement. All right. Now, do we know what these things are? Well, yes, we do, because this matrix here corresponds to, let's see if we can go back there. This matrix here corresponds to P. P is equal to the representation going from E3 to B of the identity. Okay? P inverse is equal to the representation going from B to E3 of the identity. Okay? So these two are inverses of each other. So the columns of P are exactly equal to these representations here. The first column of P is equal to the representation B of E1. That's what we get from right here. And we can look back and see what P is. The first column was 1, 0, 2. The second column was minus 1, 1, 1. And the third column was 0, minus 1, 1. So minus 1, 1, 1. And I'm not sure if I remember this correctly, but something like this. Okay, so if we so the representation of E1 with respect to B is the first column, and we could do the same with the other columns. So it turns out that the eigenvector of S is exactly equal to the representation of the eigenvector with respect to T in terms of the new basis. Okay, so this is how eigenvectors transform from one representation to the other. In order to get an eigenvector for a new representation of a linear transformation, all you have to do is take the old eigenvector, change the representation, and that will give you an eigenvector for the new matrix. All right, so how do we compute eigenvalues and eigenvectors? We're going to make use of this fact. Okay, so let's suppose we start with a 3 by 3 matrix, and we want to find a eigenvalue that satisfies this equation. T times some eigenvector is equal to some scalar value, which could be real or complex, times the eigenvector. Okay, now we've actually done this before. We write this out and we do some algebraic rearrangements, and we get the following result. Okay. Now, this turns out to have a solution if and only if this matrix is non-singular. I'm sorry, if this matrix is singular. Notice this is a homogeneous equation, so it only has a solution if the matrix is singular. The only way that the matrix can be singular is if the determinant is equal to 0. Okay. Now you can use 3 by 3 formula of the determinant, or use Wolfram alpha or something, and you get a polynomial expression in terms of the unknown x. Notice that this is a cubic polynomial for a 3 by 3 matrix. And it turns out that this can be factored. Now when this can be factored, we know that the solutions for the determinant equal to 0 will be the roots of this polynomial. So we get 5, 4, and 2. Those are our 3 eigenvalues. Once you have the eigenvalues, let's find the eigenvectors. Well, plug in these values successively. For each one of these values, you're going to get a homogeneous equation. And the homogeneous equation is guaranteed to have a solution because we chose these eigenvalues in just such a way that this matrix is singular. And like I said, if you have a singular matrix, then you're going to have a solution to the homogeneous equation. Just use plain old Gauss's method, and you'll get a solution. Now notice this is not the only solution. Any scalar multiple of this vector will also always be a solution. That's always the case with eigenvectors. If you have an eigenvector, any multiple of that eigenvector is also an eigenvector. Okay, so here we have the eigenvector corresponding to the eigenvalue 5. We plugged in 5 for x and got this result for our solution. Now to find the other eigenvectors, you just plug in these other values and you'll get an eigenvector for the eigenvalue 4, an eigenvector for the eigenvalue 2. And that's what he does here. Plugs in 4, you get a solution, and plugs in 2 and gets a solution. The same technique. Okay, let's do another example. Suppose we have eigenvalues and associated eigenvectors for this matrix. So let's start with the same equation. This is the equation that defines eigenvalues. Do the algebraic rearrangement that puts the x on the diagonal. In order to get the determinant equal to 0, we get some polynomial. In this case, the polynomial is a quadratic polynomial because the matrix was 2 by 2. It turns out that the two roots are x equals 2 and x equals 4. So let's plug in x equals 2 and to this equation and solve. That will give us one eigenvector. Then plug in x equals 4 in this equation and solve. We'll get another eigenvector. Okay? And that's exactly what he does here. Turns out that the first eigenvector is some constant, is the solution like this. What this means is that V2 is equal to, since B2 is equal to minus B1, I could choose B1 equal to 1. So so here we have 1 minus 1 times any scalar multiple. So I have 1 minus 1 times k. All right, in this solution, when you do Gauss's method, and you get the solution in terms of B1 and B2, I could write this as V4 is equal to any scalar multiple times 1, 1, because the two components are equal. So that's 1, 1 times k. Okay, so we get the same result as we did before, that the solutions are equal to some particular vector times any scalar multiple. Now, I could have chosen 2 minus 2, 3 minus 3. I could have chosen minus 1, 1. All of those are correct answers. All of those are eigenvectors. All right. Now, in the case when the matrix is upper diagonal or lower diagonal, then it turns out, we didn't talk about this, but it turns out that if you have an upper or lower diagonal matrix, the determinant is equal to the product of the diagonal entries. Okay. So here we have the determinant of this matrix is just the product of these three values. So in fact, the eigenvalues are simply equal to the diagonal entries of the matrix. If you take lambda 1 equal 3, plug it in, it turns out you get this for your most general solution. If you take lambda 2 equal 2, you get this for your most general solution. Now here we have an unusual case, because usually what we've seen before is that if you have a 3 by 3 matrix, usually you have 3 eigenvalues, and the 3 eigenvalues correspond to 3 different eigenvectors. Here we only have 2 different eigenvectors. All right. Now you can see that in these computations we've been using this particular computation, the determinant of t minus x times I. All right. When we computed the eigenvalues here, we took the determinant of t minus x times I. We did the same thing back here. We took this t minus x times I. We did the same thing back here. We took the determinant of the matrix minus x times I. So this is consistently what you do in order to find eigenvalues of a matrix. So we've seen also that when you take this determinant, you always get a polynomial in x. So we just, in order to make things simple, we define this polynomial as the characteristic polynomial of the square matrix T. Okay, so characteristic polynomial is the polynomial you get when you take this determinant equation that determines the eigenvalues. The characteristic equation is the determinant of t minus x times I is equal to 0. And the characteristic polynomial of a transformation is the characteristic polynomial of any matrix representation. It turns out that any representation of the same linear transformation will have the same characteristic polynomial, no matter what basis you use. Okay. So we can use this to prove a lemma. A linear transformation on a non-trivial vector space has at least one eigenvalue. Okay, so how do we prove that? So any root of the characteristic polynomial is an eigenvalue. Over the complex numbers, any polynomial of degree 1 or greater has a root. Now this doesn't say it has a real eigenvalue, so this eigenvalue could be real or complex. Okay, so this result is why we switched in this chapter from working with real number scalars to complex number scalars, because we want to get this result that we can always find an eigenvector for any matrix. Okay, so let's talk about eigenspaces. Basically, eigenspaces are the spaces spanned by eigenvectors. If you have vectors, they determine a vector space through their span. So the eigenspace of a transformation T associated with the eigenvalue lambda is basically the set of vectors spanned by the eigenvectors. Well, actually, that's not how it's defined this way. This is the set of all eigenvectors corresponding to the eigenvalue lambda. Okay, so that's how we can define this, that the eigenspace is the space of all eigenvectors corresponding to the eigenvalue lambda. Okay, so in this example, when we had three eigenvalues and three separate eigenvectors for the different eigenvalues, we got three different spaces. All of the vectors along the 1, 1, 0 direction, that was our first eigenspace. All the vectors along the minus 7, 7, 1 direction, that was our second eigenspace. All these vectors form the third eigenspace. So you can see that these are actually vector spaces because these are one-dimensional vector spaces. Okay, so we need to prove that an eigenspace is a subspace in general. In other words, the set of all eigenvectors corresponding to a particular eigenvalue forms a subspace. And this has an algebraic proof. If we take a particular eigenvalue, first of all, we notice that 0 is always in this eigenspace because t0 times 0, which is always equal to lambda 0. Okay, so the eigenspace is non-empty. What remains to check is closure on the set of linear combinations. So if we take any collection of eigenvectors corresponding to this eigenvalue lambda, and we want to show that this linear combination of eigenvectors is itself an eigenvector. So let's apply the transformation t to this linear combination of eigenvectors. Okay? Since t is linear, we can break up term by term. And then we can use the fact that each individual zeta is an eigenvector to show that t applied to zeta 1 is lambda zeta 1, all the way up to lambda to zeta n. T applied to zeta n is equal to lambda times zeta n. And then we can factor out the lambda, which is common to all of them, and we can see now that this vector, t applied to this vector, will give us the eigenvalue lambda times the same vector. Okay, so in fact, this linear combination of vectors is itself an eigenvector. And that means that it's in the space of all eigenvectors corresponding to the eigenvalue lambda. So in fact, the eigenspace is a subspace. Okay, now we have a theorem. For any set of distinct eigenvalues of a map or matrix, a set of associated eigenvectors, one per eigenvalue, is linearly independent. Okay? All right, so if we take a number of different eigenvalues of a map or a matrix, and we take one eigenvector corresponding to each eigenvalue, then this set of eigenvectors is linearly independent. Okay, so if I take, for instance, if I take three vectors, 1, 2, 3, and each one of these three vectors corresponds to a different eigenvalue, then these three vectors must be linearly independent. Okay, we can use induction on the number of eigenvalues. Okay, the base step is there's 0 eigenvalues, and the set is empty, so this is linearly independent. So let's continue. Okay, so let's assume that the statement is true for any set of k distinct eigenvalues. All right, so we're starting out with k distinct eigenvalues, and we're assuming by the inductive hypothesis that the k eigenvectors corresponding to these k distinct eigenvalues are linearly independent. So we're assuming that v1 through vk are linearly independent. And we want to show that if we add one more vector with a different eigenvalue, then the set of vectors is still linearly independent. Okay, so if we add one more vector with a different eigenvalue, we now have eigenvalues lambda 1 through lambda k plus 1 because we've added another vector. And our eigenvectors are v1 through vk plus 1. Now let's suppose that these vectors now are linearly independent, or linearly dependent rather. Let's suppose that once you add this new eigenvector, you get a linear dependence relation. And we'll write that linear dependence relation here. Okay. All right, now let's take this equation and we can apply we can do two things to this equation. First, we can multiply both sides of this equation by lambda k plus 1. All right, then the 0 stays the same. We've simply multiplied every vector by lambda k plus 1. The second thing we can do is apply the map t to both sides. Now, t on 0 is 0. And if we apply t to each vector individually, well, these vectors are eigenvectors. So t on v1 is lambda 1 v1. T on v2 is lambda 2 v2. All the way up to t on vk is going to be lambda k plus 1 times vk plus 1. All right, so we have two equations that involve linear combinations of the eigenvectors here. Let's subtract the two equations. Notice that this one has a v1, this one has a v1. If we subtract these two equations from each other, we can factor out the c1 v1, and here this one has a lambda k plus 1, this one has a lambda 1. So the difference between these two terms exactly gives me this term here. If I do the same thing with the terms involving v2, I'm going to get similar c2 times lambda k plus 1 minus lambda 2 times v2. So I can do that all the way up to ck plus 1. Now when I do ck, I'm going to get lambda k plus 1 minus lambda k, because from this expression down here, I'm going to get ck lambda to k vk. Then in the last one, notice that I have lambda k plus 1 from both of the two equations. So this is going to give me 0. Okay. Now look at this. Here we have a linear combination of v1 through vk that turns out to be 0. Furthermore, we know that lambda k plus 1 minus lambda 1 is not 0. Lambda k plus 1 minus k is not 0. So we have that. Now, we know that v1 through vk is linearly independent. Linearly independent. The only way that these can be linearly independent is if all of these coefficients are 0. So this must be 0. This must be 0. Now, if we focus on this one in particular, how could this coefficient here be 0? Well, we know that this part is not 0. So that means that C1 must be 0. C1 must be 0. Similarly here, we have a linearly dependence relation. We know that this coefficient must be 0. This one is not 0. So this ck must be 0. And this argument holds for every single coefficient in this sum of eigenvectors. Okay? So we've concluded that, in fact, all of these coefficients are 0. Now, once all of these coefficients are 0, we can plug that back into here. Here we have 0 equals ck plus 1 times lambda k plus 1 times vk plus 1, which means that ck plus 1 must also be 0. So what have we shown? We've shown that if there is a linear dependence relation among the k plus 1 eigenvectors with different eigenvalues, in fact, all of the coefficients must be 0. It's the trivial linear dependence relation, and we cannot get a non-trivial linear dependence relation among the k plus 1 eigenvectors, which implies that v1 through vk plus 1 are linearly independent. Okay. So we've gone from the induction step that v1 through vk are linearly independent to the conclusion that v1 through vk plus 1 are linearly independent. Okay. Now this has very profound consequences, because now if we have 3 distinct eigenvalues for a 3 by 3 matrix, we know that the 3 eigenvectors are linearly independent. Now, since they're linearly independent and there are 3 of them, they must form a basis for R3. So here we automatically get a basis for the vector space as long as the eigenvalues are distinct. Okay. All right, now in this case, we don't have distinct, we only have 2 eigenvalues. We can get 2 eigenvectors. This is not a basis of 3-dimensional space, even though it is it's a basis of a subspace, but it doesn't give us a basis of the entire space. Okay. All right, so an n by n matrix with n distinct eigenvalues is diagonalizable. So if we have n distinct eigenvectors, n distinct eigenvalues, we have n distinct eigenvectors that are linearly independent. Okay, so let's go to see what Lemma 2.4 is. And Lemma 2.4 exactly says a transformation is diagonalizable if and only if there's a basis n scalars lambda. Now these lambdas are basically the eigenvalues corresponding to these eigenvectors. So transformation is diagonalizable if and only if there's a basis of eigenvectors. And that's exactly what we've shown here. That if the eigenvalues are all distinct, then there is a basis of eigenvectors. And that's it for this section.